study session, the AP Physics final. Here we go. Guys ready? So it was requested to do the study guide. We have a little statue, okay, on a platform. And theta, which is over here, is equal to 31.0. 31.0 degrees. And so I guess the question is probably asking is how much force is on the arm? So A, determine the tension on that armature that's holding it, and determine the horizontal component force. Oh, not too bad, right? Okay, so let's tackle this. So first of all, the mass of this object, 4.53, thank you. 4.53 kilograms?
Yeah.
That was very convenient to give us in kilograms, right? All right, so here's the deal. T is the tension here, and what's sweet is we do have gravity coming down, Fg, all right? And since we could kind of figure out this component right here, okay, this angle, theta, is right here. They're equal to each other. So this is cosine theta, right? This would be the x component for cosine because it's the adjacent. So Fg over T. This is our resultant. So T equals Fg cosine theta, and that will give us the tension for A, for question A. So 4.53 kilograms, 9.80 meters per second squared over cosine 31. Okay, somebody got the answer already? 51.8? Okay, 51.8 newtons. Okay, and then we'll get to 3 sig figs. Now to do part B, it wants just the horizontal component, so that's this portion right here. Well, 90 degrees minus 30 degrees, right? So 69 degrees, right?
Wait, how come you're doing that?
Because now if I know this angle, I can get this component. I know T, I know Fg, I could either use tan theta, or I could use, sine.
Yeah.
Not sine, I could use cosine again.
It's 59, it's not 69. Right there, the 99 is 39.
So yeah, carry the one over, yes, sorry, 59. Thank you. All right, no problem. Now, so we could do either way. So B, all right, we know the tension, we know Fg, we could choose either one. So I can call this beta. So now to get this horizontal component, I'm just going to call it A. So in this case, it's going to be, I'm going to use tan. So tan beta equals Fg over A. So A equals Fg, and I'm saying A is equal to the horizontal component. I could have called it A, X. Okay? So this is going to be tan beta.
Beta
is the 59. 3 kilograms, 9.80 meters per second squared over tan 59 degrees. And if somebody's got that answer, that'd be sweet.
26.67.
26 point what?
67.
6, 7, so that's 7, 3 sig figs. Okay? So that's how you get that one. We could skip to the tension. We could skip to the tension if you guys want. Since this is like tension, we could do a tension problem. And I kind of thought of this one this morning, so let's see how this looks, right?
Okay.
Can I erase this?
No.
Okay, you got it. And it's nicely on the camera. All right, here we go. So let's say we have a hanging mass. So here's somebody decided to, here's a ceiling and a wall. They're 90 degrees, right? And let's say there's a cord coming down here and a cord kind of off to an angle and a weight hanging and some weight. I'm going to call this weight M, some mass. I'm going to say this theta is like, how about 65 degrees? Is that good? And just to make things kind of interesting, let's say the angle to the horizontal right here, I'm going to call it theta 2. Let's say that's equal to 25 degrees. So now we need to find the tension in the first chord, the tension in the second chord, and the tension in the third chord in respect to M.
Okay.
Okay? What?
What's the weight of them?
I don't know. It's just M. So basically you're creating an equation, a generalized equation. And so let's say you're an engineer and a client, an architectural engineer, and some client wants different masses. You can now figure out what the tension is so to buy the right material. I'm just using that as an example. Okay? So, a couple things. I would probably first tackle the x direction. Why? Because here we're going to have 3 y directions. One going up for T1, one going up for T2, and then T3. And we could do a substitution, which I taught you guys prior. You could do a substitution with the x direction. So if I sum the x direction, fx, okay, and since this theta is, these two are equal to each other, I'm going to call that theta 1, okay, parallel lines, that angle is going to be equal to that angle. Heck, you're going to have T1 negative, since cosine's negative in this direction, cosine theta 1 plus T2 cosine theta 2. Okay, and since this isn't moving back and forth, there's no acceleration, this thing equals 0. That's going to make life way easier. So I'm going to solve for T2 just to get rid of that negative.
This result, how come the T1 is negative?
Because cosine, I put an axis here. Actually, let me just do it in black.
Oh, it's going down.
So I'm going to put an axis right through here. Okay, an axis. So if this is 0, it's going to be negative here, because cosine represents the x direction, right?
Okay, I got it.
And I'm keeping everything kind of in the coordinate plane. So solve for T2. So T1 cosine theta 1 over cosine theta 2. All right, I can use this for a substitution in the y direction. Right. So in this case, and actually let me do it in purple so as to colorize this. So sum this up in the y direction. So this component, which is sweet, they're all going to be positive. So this is going to be T1 sine theta 1 plus T2 sine theta 2 minus FG for the 3. Or heck, I'll just go T3 because it'll be the FGM. And since this thing isn't moving up and down like an elevator, it's going to be equal to 0. We could easily do elevator type problems with something like this. This could be in an elevator, this could be an elevator, and then we just need the acceleration going up, and you would plug that in here.
Yes, then you would solve for the acceleration.
Right, but since we're not doing that, let's work with this. Is that cool? And two, if it were an elevator problem, we have to account for the mass of the box, the mass of the cords. You get the idea?
And T3 is negative because the weight is pulling that down.
They're pulling it down, right? These guys have to exert a force this direction, real quick. The tension in the cords have to be pulling upward. There's more to this. I mean, we would have to account for the tension in the walls, but we're not doing that, okay? I just wanted to, because there is some force going this way, there's some force going that way, I'm not accounting for it. We're neglecting that, okay? For the moment, I just wanted to spice up the problem. So what's going to happen is, rewrite this, T1 sine theta 1 plus, I'm going to take what's in blue here, but T1 cosine theta 1 over cosine theta 2, and there's something that's sweet to this. Yeah, the sine theta 2, you're going to have here tangent. And I'm going to put T3 on the other side just for making my life a little easier for now. Are we good? Now, I'm going to rewrite this one more time. And actually, you guys know that this is going to be tangent, right? Okay, so I'm going to factor out T1, parenthesis, sine theta 1, plus cosine theta 1 tangent theta 2 parenthesis equals T3. Okay? So T1 equals T3 over sine theta 1 plus cosine, oops, I'm going to put that in blue just to keep it colorized, and you guys can visualize it. And tan theta 2. Okay?
And T3 is just mg, right?
So, and it's just going to be mg. So you could, and we could write mg for now.
Yeah.
Keep everything in terms of mg, and then we could put values later.
Yeah.
Okay? So I would just get this, and I would get this in whatever form it's going to come out. So this is going to be mg sine 65 plus cosine 65 times tan 25. These are all degrees. I would get this answer. I would just put that over 1, and I'm going to do it also to make sure we all agree. So 1. So sine 65 plus cosine 65 times tan 25. You don't know the mass. The mass is just m. Okay? And so what I'm going to get for an answer, and I'm going to go to 3 sig figs for now, because we're 2 sig figs, right?
Yeah.
We can, when we formalize it, we'll probably put the, when we formalize it, we'll put the answer that we would in correct sig figs in with our remarks. So this is 0.906 mg, just for now. We can multiply the 9.8 or times 10 later. Okay?
1.1.
And this is over 1.
Oh, so what?
Yeah, this is over 1. It's a fraction. So what I did is I moved this out and made this 1 over this whole thing.
You should.
Okay, take a look. What I did is I'm going to erase this up here, but I put the mg over here, T3, I put it over there, so this is 1 over the sine 65 plus the cosine 65 times the tan 25. And that's how I got the 0.9.
Okay.
Okay? It's a fraction. So I just factored it out so I have a value. So now I have this in terms of mg. And if I took g as 10, really this is just 90.6, right? No, not 9.06, because it moves the decimal over 1, sorry. Yeah.
So, like, I don't know, maybe you're getting to this, but should you replace G with 9.8 so it's just M?
No, it is M. You're going to have to keep the M. The M doesn't go away, okay, folks? Don't get rid of the M.
I see. So you just...
You could do the G if you want.
But you don't need the G in there.
I'm just going to save it for now for ease, and then for my final answer, I'll put everything in a nice little value.
Okay.
Right? Because what's going to happen is I'm going to take this answer. Now I know T1, I'm going to put it up here. That's why I need to erase that so there's plenty of room. So I'm going to take this value and put it up here. See, and I'm going to have everything in terms of M. Okay? And that's a valid question to ask of you guys. AP, just create a generalized equation so that you can answer. I mean, it's not far-fetched for one client to want something and another client to want something different. I'm talking engineering-wise. So knowing how to create a general equation is great. Okay, so equals. So I'm going to take this answer and I'm going to put it up here. That's why I went to 3 sig figs for now. mg cosine, so it's cosine 1, so this is going to be 65 degrees, over cosine 25 degrees, okay? Let's get that answer. And it'll be terms of mg for now, and then we'll put in correct value. So 0.906, whoops, I'm going to make this a fraction. 0.906 times cosine 65 over cosine 25 and 0.422. So I got an answer of 0.422 mg. Okay, and so now you would write, it would be nice to write what they're equal and then write a nice little statement. I'm not going to put a statement for now for time. But, so now T1, you know, it's 0.906 mg. Well, I'm going to multiply that and put it to correct sig figs. So 0.906 times 9.8. 8.9?
That's what I read too.
8.9 M. T2, 0.422 mg. 0.422 times 9.8. 4.1 M. And then T3 is going to be negative, it's downward, right? So minus 9.8 M. And we all have meters per second squared and all that. But these are the values that you would write down, and then you would write a little statement or something to indicate what the tension is. And you should, what?
Would it be meters per second?
Yeah, meters per second, you could do that after. Okay, in your statement, you could put 8.9 meters per second times some mass in kilograms, so you could state that clearly so that people understand. Okay, and let's see, does this make sense? So tension 1 is closest to something that's going straight down, right? about 65 degrees. This one isn't. So this should have the greater tension. Sure enough, it has the greater tension compared to 2. And since this one's downward, yeah, so everything makes sense. Are we good? Because we know that a chord, to make sure if we got a chord that's closer to horizontal, not as much tension as straight up and down. Is that good? All right. Does anybody need to take a picture of this? I will move aside. Isn't it elegant? I just enjoy watching algebra come together. I'm sorry.
Doing this with calculus would be so much easier.
What?
Some of the physics stuff with calculus.
Actually, the calculus is better. We're doing algebra based. When you leave PHS, you will see how much. If I have time, I'll show you a book where the calculus is in there, especially with E&M, electricity magnetism. It's sweet, but you need to get your calculus under your belt, doing that algebra that goes with the calculus. Once you have that, life just explodes. It's elegant. Okay, let's get this out of the way. So we're going to look at a center of mass, and let's do this. This is going to be conceptual. Then I want you to think about a couple things, all right? So this is a kind of a center of mass problem, kind of thinking conceptual. So we shoot a rocket, okay? So a rocket gets shot. So this rocket takes off, and right here at midpoint, the rocket breaks in half. So maybe I should do this rocket kind of like a double. No, that's not going to. Let me see. Let's do a rocket like this. I'm trying to kind of make a better visualization. That was the Enterprise, and that wasn't going to look good. I'm just going to make it a rectangle. Here's a rocket. It takes off. Okay, it's moving forward. And right about here, this rocket breaks up in half. First of all, let's say the rocket's equally balanced. So where's the center of mass here? At the center. How would you test for center of mass of any object?
Hanging.
The hang test. Okay? You just, like here's this calculator, and then you draw a line straight down, vertical. Then you would go like this. It doesn't matter where you grab it. Then you do this. Drop a line, and where it crosses, that's your center of mass, which I can I got it. Okay, so the center of mass of this calculator is right here. If this calculator were to break in half, right, where would the center of mass be? Okay, good. It's still, yes?
Isn't there an equation to solve it with the Riemann sum?
Yeah, but
Yeah.
let's go right here. Okay, this is all conceptual for now. So the center of mass is still where? Good. So let's say this rocket, okay, so what is the trajectory of the center of mass for this object, this rocket that just broke apart? It's still a parabola?
Yes.
Beautiful. So still a parabola. I like that. So let's say the pieces now go further apart for some reason they have. So, and I'm going to put the arrow still here because that's the rocket. Where's the center of mass? Still on the parabola. Sweetness. You got it. So even if the rocket goes way out here, just for the sake of, and I'm going to try to keep it somewhat even. So where's, a little further out. So where's the center of mass still? Parabola. Okay. What else do you know about that center of mass? What about the motion of that center of mass? Think about it. In the x direction, what is the motion of that center of mass? What, the velocity is constant. It's equal to what? Its original motion. These obviously had to do what? What happened when this broke apart? What's happened to the velocity for both objects? It's changing. It obviously did what? Did it decrease or increase? Increase. Because if it didn't increase, it was just an object that just broke apart, they would pretty much what? Fall apart. It would pretty much just fall apart, right? And just stay in the same trajectory. So the velocity in the x direction, both for the objects that broke apart, for the rocket, and for the center of mass would remain the same. But in this case, for sure, definitely maybe there was a thruster, and these guys just started blowing apart, right? They're increasing, but the center of mass, what happened to it? It remained the same. It remained constant. Are we good with this?
Yeah.
Okay, that's good. Yes.
Like that be on the test?
What?
Will a question like that be on the test?
What?
Yes.
I don't know. It might be, it might not be. I'll tell you for one thing for sure, since we learned some center of mass and the AP test is going to have a center of mass, guess what I'm going to do? I'm going to put a center of mass question on there.
Maybe a non-conceptual center of mass question.
A math, there's no math. No, I'm not going to put a math.
There is an equation.
Yes, sir.
There is an equation, but I'm not going to put it. I'm not going to put on the. There's none on the AP test, and there isn't. Yeah,
It's all conceptual.
all conceptual.
You don't need to know the equation.
Don't need the equation. That's AP Physics 2. The only reason I taught it in class, or had you guys do a basic equation, is to introduce and get you guys to have a feeling for it. I mean, it won't be. I mean, all I would do if I were doing this to find the center of mass, I would make this the 0. And I would multiply, the total mass, center mass, its distance. Then I'd make this and then find this distance.
Yeah.
Then I would divide it out. The equation is like mass, x center of mass equals mx1 plus mx. Yeah, this is 1. This is total. 2, x2, you get what I'm saying? And this one I'd make 0, bring this over, and you'd have the center of mass, its distance. Okay, that's a generalized equation, and it's also in your notes on Google Classroom. Yeah, Danny?
Is there any way we can do another study guide problem?
Yeah, we're gonna, so wait. So we did tension, we did center of mass, let's do a chase problem.
Okay.
Okay? And 2 types of chase problem.
Please.
Oh, wait.
Yeah. Take a picture. All right. So is it all right if I erase this? Oh, okay. Real quick? No, it's fine. Actually, I'm going to move out of the way, and I'm going to do this. A little H2O. Now can I erase it?
Yeah.
Oh, I thought she was going to take a camera. Okay. So, let's do this. So let's say Mary, and I'm making these up, okay? Just for the sake of. Mary can run 2.5 meters per second, just for the sake of this, right? Jim is 10 meters ahead of Mary, okay? And he, because I'm going to assume Jim is a he, okay? And Mary is a female for the sake. And he can run, 3 meters? Okay. 2.3 meters per second, just for the sake. At what time and distance? At what time and distance does Mary catch up to Jim? Time and distance does Mary catch up to Jim? So could you guys graph this real quick? Could you set up a graph? A PT graph. Because you guys are going to have to know your PT graphs. And I put questions that are pretty intense with those PT graphs. Sorry. I get paid to do something. All right. And I also...
Draw one as well?
What?
Can you draw a PT graph as well?
Sure, let's do a PT graph. So I would tackle... The PT graph is great to draw. So what would so like Jim's setup, how would you set up Jim? First of all, what goes on the y-axis?
Velocity. Position, I should say.
P, okay. So positions on the y-axis and T times on the x-axis. Okay, so how would you set up Jim? Just a generalized sketch. Is he a horizontal line?
That's the slope.
He has a slope. What is the slope?
2.3.
The 2.3? Yeah, he has a slope. That's
He doesn't start at 0, right?
Does it, who?
He doesn't start at 0.
What does he start at?
10.
And are we going to, I said ahead, so in thinking ahead, what does that mean to you? So what does that mean to you, ahead? Is that a positive direction or a... You see, you could do negative, but I'm just going to go, yeah, negative. So that means probably somewhere right there. And you could write 10 meters if you want. And so you can just do a general sketch of the slope. Actually, I'm actually going to make it a little shallower because he's not as fast as Mary. And so what is Mary?
Slope of 2.5.
Yeah, and starting at, so Mary's at the origin. Kind of something like that. So what we're trying to do is find this time and eventually this distance. So they share what? A common data point, right? So the first equation, and I'm just going to set up let's set up the first equation.
Could you find this with your graph? Yeah.
You could graph that on the calculator and find it, but no. We're better than this, right? We're better than this. We can do this math-wise and go like this. They're going to share the same P. So P equals, so for Jim, for this equation of this line, what does Jim's equal? Actually, I'm going to put P sub J for Jim. So what is this equation? Well, how would you write this equation for Jim?
2.3t plus 10.
Real loud.
2.3t plus 10.
And I would go 2.3 meters per second, T, plus what?
10.
Times?
Plus 10.
Plus 10, yeah. Thank you. 10 meters, okay? Now, what are you going to do for Mary?
2.5 meters per second.
There we go, 2.5 meters per second, T. There is no y-intercept is 0. So what do we know for sure for this point? Set it equal to each other. Pj equals Pm. So 2.3. And is it all right if I just take the units out for now? So 2.3 T plus 10 equals 2.5 T. And let's solve for T.
T equals 50.
So I'm going to go 10 goes on this side, 2.3 subtract that, 0.2 t. Am I right? And then t equals 10 divided by 0.2. And this is going to be in seconds.
50 seconds.
You got the answer? 50? 50 seconds. Now, how are you going to find the position? I hope you guys... What?
Plug it in.
To what?
To any equation.
Which one?
Either one.
I plug it in that. Yeah, I just go 2.5. So P, 50. And what do we got for a distance?
125.
What?
125.
Meters. Okay, you got your time. So not bad, right? You could do this one. So let's do a different one.
Well, there's
I have another question. If we decide to graph it on our calculator, not saying that we will, just if somebody does, would you mark them down for it, even if they got the correct answer?
So what do you think I'm going to want on the test?
You want work shown?
I want the graph, and I want what else? The work shown. And I want a nice little explanation. The calculator is not your brain. It's the tool. This is a tool. I want everybody around the world. A calculator is a tool. Okay? What's in your head is more important, how you explain it. That's what the AP folks want too. Hello. Yeah, if it's just a calculator, I'm not going to dock points because I don't know what the calculator did. I want to know what your brain did. Okay, so wait, hang on. Yes, sir.
there was a problem number 49 on the study guide that was really similar.
Yeah, well, yeah, I'm going to... 40?
I was just saying, like, if you wanted to do it.
Let me see.
But I have a question.
Hang on, Chief. Let's see what this young man is saying here. 49?
Yeah.
This is the first study guide that I gave you guys that doesn't have a...
It's the two bars heading in there.
Yeah, it doesn't have a key complete.
I think it's the same.
Oh, this is the same as what we did. I don't want to do that one. I'm going to change it up.
Ask me for a brief question.
Yeah.
So for that one, for the position versus time graph, would they be heading towards zero?
What?
Like if you made 0 the x-axis petaluma, would they be heading toward?
Oh, if you want to go towards, you could start it from the negative up, and away you can make it positive. So you could go, here's Petaluma at 0. So you could say, if you want to kind of use Santa Rosa's north, right? So you could go 10 miles up, or 10 kilometers. Then you want to say from San Francisco minus, which would work. Yeah, you can orientate that any way like that. Or if you make San Francisco 0 and Petaluma up further, you know, you have to figure out the orientation. Just to make sure you explain clearly what you've done. This explains quite clearly. We said that, hey, Jim's 10 meters ahead. Now let's do this one. Just a simple one. And if Danny doesn't mind me using him as an example, is that okay, Danny?
I do not mind.
Or should I use somebody else?
I don't mind.
I can make me faster than Daniel.
Okay. So Danny had a lovely evening. Lovely evening. He went off on a nice date. Just got great thoughts on his head. Should be paying attention while driving. Okay? So let's say Danny, okay, is driving, I'm going to say 15 meters per second in a 10 meter per second zone. Zone. So he's going 5 meters over. I'm just making this up so he's going 5 meters over. So he passes he passes Sally, the cop. Okay? At the instant, okay? At the instant, Danny passes Sally. Sally passes Sally. Sally starts to accelerate. Starts to accelerate. Oh, she starts to accelerate at,
At least 30 meters.
oh, that's too fast. I'm just gonna, I don't know, 4 meters per second. That's gonna be pretty fast. Because it's, yeah, you know what? Let's really make it slow. 1.5 meters per second squared. I'm gonna go with this. Okay. At what distance and what time? Okay. At what distance and I can spell, and time does Sally catch Danny? Okay? At what time, at what distance and time? So it's the same thing. So here, you're going to need to use your distance equation, okay? Which one?
V naught yt plus 1/2 at squared. Delta x equals v
Or
naught.
the VS squared equals 2.
Yeah, it is.
No, I wouldn't use V. Because you're looking for what? Distance and time. So you're going to use an equation that has distance and time.
The displacement one does have.
Yeah, the displacement one. So I would go like this. X final, use a switchblade one I like to call it. X final equals X naught plus V naught T plus 1/2 AT squared. And you need to set it up for each. The last chase setup was all linear. Hey, Danny's being linear because he's got his head in the cloud. Ah, I'm excited. Oh, it's such a wonderful evening driving along. Right? Or riding a bicycle along. I don't know. It's pretty slow. Well, maybe, I don't know. It's fast, slow. I don't know what that is. Okay. I'm just going with it. So let's set up for Danny. So let's set up the equation for Danny. So we're not going to worry about that. That's 0 because that's at the point. So if you were to graph this, okay, a position time graph. So P is up here, T is over here. Let me see if this is within the frame of the, yes. Okay, so let's look at Danny's. What position is Sally the police officer? Is it the 0 position? Yeah, it's the 0 position. So this is 0. So Sally's 0. When Danny starts to pass Sally, what position is that? 0. So for Danny, he's starting at 0. What type of graph is his going to look like?
Linear.
Linear. So it's just so if you what? Ah, see, and let's take a look at this. Does Danny have acceleration? No, 0. So it's going to be this equation. So x Danny is going to be, this is 0, x naught. So for Danny, it's velocity Danny times time. For Sally, x Sally, okay, and you said it was a parabola, you're correct. She doesn't have an initial velocity, it's 0, her distance is 0. It's going to be this portion of the equation, so it's going to equal 1/2 AT squared for Sally. So, and now let's take a look at this, guys. We've done these earlier on in the year. So what's going to happen is at some point here, they're going to have a similar T and a similar position. They're going to have the similar distance. So that means what? These two are going to be what to each other? Equal. Just like the other equation. It doesn't matter. And we could have had two accelerations. Two different accelerations, and we can have a curve that meets also. So x Danny equals x Sally. So v Danny t equals 1/2 a, and I'm going to call it as for Sally because it's her acceleration. Okay, and then t squared. Okay? So, oh, sweetness. Look at this. This t is going to cancel. This is going to cancel. Put a 1 there. Okay. Let me rewrite that so it looks nicer. So I'm going to take the 2. I'm going to take that and put a 1 above it. Okay. So there's only time. So rearrange this. So t is going to equal 2v Danny over a Sally. The acceleration of Sally. So the velocity of Danny over the acceleration of Sally. Let's plug in these values. I don't know what it's going to be like. So Danny, 15 meters per second. Sally, 1.5 meters per second squared. Okay? Somebody got that already? So 30 divided by 1.5? 20? 20 seconds?
Yes.
Or actually, for sig figs, because we're 2 sig figs, right? Except for the, 2 sig figs. So 2.0 times 10 to the 1 seconds. So now we know the time. Now, which one are we going to do for the distance?
Easier one.
Easier one. Yeah, I'm going to do Danny's. So, Danny is what? 15 meters per second times 20 seconds. So, what, 300 meters? 350 meters? 250 meters, sorry.
300.
His is,
Yeah, 50.
300, sorry. Forgive me. I got it right. My brain's a little disconnected. It's been a long day. Not bad.
No.
I feel like I'd accelerate faster, but
Yeah, you would, but this is just for, I want to make this work.
By the way, Danny was going 54 kilometers an hour.
he's going 33 miles per hour. I looked it up.
He was going 50 miles per hour?
33.
33. Do you know pedestrians could get hurt?
That's not.
Okay, it must have been a lovely evening, right?
I have a question.
Okay, hang on. So we did chase. Okay, then we're going to do a projectile from a ditch.
Yeah. No, yeah. Can we do 55 first, quickly? Because it said 55 minutes.
So this is from not the first one, right? Not this one.
Yeah.
Just
So 55.
We're going 33 to 22. That's 11 miles an hour. Ooh.
that's annoying.
So Danny, is this the first time you've done this stuff?
Yeah.
Okay. Stops. Oh, I call this like the kind of the drunk driver problem. What is the total distance the driver? Oh, this is a great problem. You want to do it?
Yeah.
Okay, so this is 55 for those who are going to be watching from YouTube. It's 55 from that original study guide. And it's a 2-step. Oh, some people want to take a picture, take a picture. Now remember, I could have done 2 accelerations, one accelerating faster and one going slower, and where the 2 curves might might collide, okay, or meet. Yeah. And they could never intersect, that's true. That could be, hey, that person's getting away from the cop. That could happen. It can happen. You know, Hollywood style. All right, so in this case, you got a driver driving at a constant velocity of 27.3 meters, okay? Sees a boulder in front of them, and so there's a bunch of things. You guys have reaction times of probably 0.43 seconds. Meaning this is going like, oh my gosh, I'm going to hit the accelerator, I'm going to hit the brakes to stop. So there are multiple events going, okay? And so you end up decelerating, so they're going to decelerate at 8.9 meters per second squared, and you come to a stop. So what is the total distance that you're going to stop? Okay? So here's the trick to this. I'm going to put it up on the board so that people can see it. Normally, people have a reaction time of approximately 0.5 meters. Meters, did I say that?
Yes.
Not meters, 0.5 seconds, more or less. So in this case, we got the velocity of a driver at 27.3 meters per second. Reaction time of 0.43 seconds, not bad, and a deceleration, okay, and deceleration is negative meters per second squared, okay? If it was an acceleration, it's a positive. We got it?
Yeah.
Okay, so here's the deal. This total distance, this x total, is really a bunch of things. You have a distance of going, oh my gosh. See, you're at this constant velocity, and all of a sudden you decide the amount of time it takes you to take your foot off the accelerator and put your foot on the brake. So this is an x reaction plus all of a sudden your velocity is going from what? From 27 to what? 0. So you have a final, so this is an initial velocity, right? You're right, it's an initial, and you have a final of the driver that's equal to 0. Okay? So this, I'm going to call deceleration. I'm going to call it D.
Wait, shouldn't that be a B?
It's just an XD, deceleration. So let's see what equation do we want, a generalized equation that we're formulating? What kinematic equation we're going to use? Not V. We're not
The displacement one?
the displacement one. We're back to this thing. X final equals X initial plus V initial T 1/2, right? AT squared. Okay, but you know what? Do we have a time for the deceleration portion? So maybe that's why we should use that one. Yeah, you're right. So we're going to use a combo. V squared, V naught squared plus 2A delta X. Or delta X meaning XDE. Okay, so first of all here, do we have an acceleration? No, so that's going to be 0. So it's going to be this equation. So in this case, XR is just going to be V initial the driver times T, the reaction T. Okay, and then this distance is going to be a rearrangement of this. Okay, and we know what this distance is, or this velocity, that's 0. That's dropping out. That one drops out. So when we rearrange this, this is going to be XDE equals negative V, and I'm going to call it VDO squared over 2A. Okay, and
the A is the deceleration, right?
A is the deceleration. So for this part of the equation, negative V dO squared over 2A. So that's going to give us our total distance. This is the, oh my gosh, the shock. Okay? And I'm pretty sure on D Street here, a lot of that happens when people you're driving down D Street, all of a sudden people come out of the cross streets. I mean, it's happened a lot to me. For some reason, more so on D. I mean, people will just pop out a little bit because they can't see around the bushes, you know, the cross streets. Okay, so that's a good example of that. Okay, so 27.3 meters per second, 0.3 seconds, so this is our reaction time portion. I'm going to take that minus and put it here so I don't mess up. I'm going to put my fraction bar, 27.3 meters per second squared, 2 times, oh, that's interesting. Oh, that negative is going to cancel. Ah, ain't going to mess up now. Okay, so that's going to make it positive. I'm just trying to avoid people from messing up. Okay, did anybody get the answer?
53.6.
50 what?
53.6.
Meters?
54 if you're doing sig figs. Right?
Sig figs? 54 meters. So not too much of a shock. About 150 or so.
And then it's like you gauge the distance where the boulder was, and like you have to stay with
Yeah, well, yeah, you would stay, in this case,
You would just see which number is bigger.
yeah, you would see which one's bigger and if, you know, that type of thing. I used to do this mainly for some regular physics. And I can do it for AP too. If you're a drunk driver, here's the problem. If you have some wherewithal, your reaction time still drops. You try to hit those brakes. This is why people end up when you're drinking and driving, this is where you end up hitting somebody. You've extended this distance a lot. You may be drunk and have enough force to push on the brakes and skid like crazy, but the problem is you're already ahead of the game. Your reaction time for when you drink and drive, your reaction time is never at 0.43. You're sluggish. You're going to mess up. Okay, so it was one of those things I used to teach a lot to get people to understand. You don't need to drink and drive. Don't do it. Mathematically, it shows it. It's bad. Okay? It's never good news for adults or for students.
How'd you get the 27.3 times 0.43 minus that?
There's no it doesn't matter. The negative came from here, but they're going to cancel. I just didn't want a student losing the minus because that always happens. This one was still here. We knew that. Okay, let's see. We did chase. We were going to do a projectile motion from a ditch. Somebody wanted to do that? Let's do it. Can I erase this? So this gets interesting. This is going to be fun. Let's just do it. And I'll let you guys think about this. So you want to shoot a projectile from a ditch, right? So let's say, I don't know, we'll make this up. And let's say you got a cannon here or something. You're going to shoot a rocket or a cannon. Are we good? And this thing is what, 15 meters below, just for the sake? And let's say it's 65 degrees. I made that up. So it's going to shoot from here and land somewhere over here. This is going to be good. Isn't it? I don't know what to do. Let's do it. Okay, so first of all, let's give it a nice velocity. I don't know, I'm going to make up a velocity. Should I make it big so that it just kind of works? No. How about 205 meters per second? Is that cool? It should make it. 65? I think I'm going to change this to 75. I just got to make it, I want to make sure it's. So we're good? It's going to go over the wall, 75 degrees. We're going to find out where it lands somewhere out there in space. Okay, there's a couple ways we could do. How about...
Wait, is that an angle 75 degrees?
Yeah.
So we're trying to find delta x.
We want to find where it's going to, yes, let's find where it lands, and let's find out the total time. So determine total time in air, or air time, total air time. Okay, total air time. Determine the range. It's all good. Let's just do it.
Is it really?
Yeah. The problem is, I'm gonna, ooh. Do we have to give a distance here? I think so. We're going to need a distance. Yeah, we want to make sure it goes over the wall. So I'm going to make it 25.
Okay.
So let's make that 25 meters. Oh, this is just exciting.
Can you put this problem on the test after we've gone over it?
No way. Okay, so we don't know this delta x.
And that's what we're trying to solve, right?
We want the total delta x, man.
You want total delta x?
Yeah, now it has to be the total delta
Because
x.
you have to go, draw the arrow mark.
That make you happy now?
Total delta x, because it's starting at the cannon, right?
Yeah, it's starting right
You
here.
can add the 25 to it at the end.
See, Danny knows. Okay, so here we go. So we got a couple things we got to deal with. First of all, you can find the total time, air time.
Just by saying delta y equals...
Which equation, what?
Delta y. Well, your displacement for the y direction, right?
So I'm going to go for the y direction and tackle that first. So
Wait, no.
here's the...
I know differently. I'm pretty sure. Actually, wait, no, never mind. This is just on flat. This isn't a ditch.
Are you okay?
Yeah.
Can I go for it? Yeah. You're beautiful. Okay, first of all, where do you want to put your x-axis? Down here? Over there?
Up there.
I don't want to do that one. I'm going to put it down here.
Make it all classy.
I'm going to make my life happy. I'm going to put my coordinate plane right here. Okay? Reason? Watch. Y final is equal to the 15 meters positive. It's going to land 15 meters up, but downfield. Y initial is equal to 0. It starts at 0. So it's a parabola that's terminated over here at 15. I'm just going to take the y direction. So, my Vy is going to be V naught sine theta times t plus 1/2 OG, so this is going to be negative 9.8, right? Because yeah, but who programmed their calculators to do? Yeah, but you don't even need to have a program. I mean, heck, I got this little Casio, and I can do it with this thing.
Program line.
Casio's are the
Get
best.
imaginary numbers too if you want to.
Yeah, ooh,
Yeah.
With your automatic formula?
yeah.
That's awesome.
Okay, so the sweet deal to this is that I would bring this 15 over, make this equal to 0. So in other words, 1/2 9.8 is negative 4.9 t squared. 250 times sine 75, I don't know what that is, so let me get that.
198.015.
198?
Yeah.
So let's do this again. Plus 198 point what?
015, so which is 198.
02. I'm going to put more sig figs. T minus 15. Okay, because I brought the 15 over, and all of this is equal to 0, so I have a nice quadratic equation. Are we good? Does this freak out anybody? So the reason I made this minus, because gravity is 9.8. This guy became negative because it went over to this side. So now we're going to get our total time. So T equals negative 9.802
Yeah, you have an issue.
plus or minus what?
You get an issue because the square root of that whole thing,
Is negative?
well, it's 197.271, so either one will work, plus or minus will work. Like when you do the 198 point, yeah, you get 2 times. That both work.
Well, the lower one's gonna be what it crosses where it's.
The cross is here.
Yeah.
And then the other one's going to be where?
So you
Down
add
here.
the two together to get the total time in the
No,
air.
the larger one will.
The larger one is this. So we're basically, hey, we could do this. We could like a little, so that the projectile makes it. Is that good? All right, to make this realistic. So 198.02 squared minus 4 minus 4.9 minus 15. So we have no negatives here. This works out nicely. Okay, that's good. And then this is going to be negative 9.8 on the bottom because it's going to be twice that value. And what are the 2 times?
40.336.
T equals what?
40.336. How many sig figs do you want to do? Or do you not?
We're only good to 3 sig figs, so 40 point what? 40.3 seconds. And what's the second one?
0.0759.
0.059?
759.
Oh, so 5.8, right? 2 sig figs. So obviously, we're going to take this time. It's going to be 40 seconds later. Hey, that's kind of sweet. We now know that.
Then you can solve for your total, right?
Well, but let's be careful for the total. How are you going to write up your total?
Well, can't you say,
So, your total distance is going to be what? X plus 25 equals what? V naught cosine theta times t, that t. And now we're going to know where it hits up above. So this x is 205 meters per second, cosine 75, times, we're going to take that, 40.3 seconds. That'll give us x, and we could add to get the total if we want. Oh, I forgot to subtract. I forgot to subtract the 25.
Wait, why do you have to do that if you use the range equation?
Can't use the range equation. Range equation only works what?
On flat.
Yeah, when y's are both equal to each other. Y final, yeah, for just,
So then you would have to subtract the times too. Because you don't need the total time.
No, we need the total time from here to this point to get our distance x. And I'm going to subtract the 25. That will tell me what this x is. And then I can get the total distance like it asks after. Yeah, so it doesn't matter. That's okay. At least we'll know what x is. Yes, ma'am?
Where did you get like your equation?
Well, first of all, I know that this time accounts for this distance and this distance. So that means this thing is going to equal Vx cosine t to this point. And I called it T1, so I should put T1 here, sorry. Because I did call it T1 up here. So now we can find out the total distance. Did somebody get that? Or
Yeah, I already got it.
what is it?
Well, I got just the V naught XT, but I forgot to subtract the 25 from that.
So subtract the 25 so we can get that.
2115.
21.2 meter.
2000.
2,115.
Wait, 2,000.
Subtract 25.
2115.
115.
You have 2,140 right now?
That's it.
Okay. And it's at 3 sig figs, it's 2,120 meters.
Wait, Mr. President.
That's for X. And then we add 25 to get the total.
Wait. If you add 25 to get the total, wait. So then basically, to get the total, couldn't you just do?
Okay, you're scaring me. I'm going to redo this.
Couldn't you just get V naught XT to get?
No, let me do this. Danny, you're scaring me. Hang on. 205.
Yeah, it makes no sense. Yeah, it makes no sense. If you're just-
I'm just finding X. I didn't, oh. Poop.
We got 2,113.
Delete 7.
I got 2113.
Yeah, hang on. I got 2138
Yeah, so that's
meters. So that's what delta X is.
more.
That's what delta X is. And if we want the total distance like it's asking, so you add the 25.
Then why do you have to subtract 25 in the first place?
I don't know, I did it because I wanted to know X.
Wait, what?
You're true, I didn't need, that's true.
I wanted the actual range.
Oh, you didn't have to subtract.
No, you didn't, but I did because I just wanted to.
So wait, the actual, you didn't actually subtract 25 then.
Yeah, you don't need to. But since I want to know, I should have said,
You didn't need to subtract.
what distance above ground does it go, and then,
Okay, gotcha.
okay? So,
Tomorrow, right, Mr. President?
so I think we covered everything.
First tomorrow?
What?
T-shirt?
Oh, t-shirts, must have t-shirts tomorrow. T-shirts.
Like,
Okay, hang on, all right, we're done?
at the very least 7.
Guys, study and keep reading about physics.